Welcome you to this lecture of microscale transport process. What we have started discussing in the last class is electrophoresis. We completed our discussion on this electric double layer and electroosmosis process, and while concluding I said that it is that there is another such electrokinetic movement, electrokinetic motion which is possible by the mechanism which is referred as electrophoresis. In electrophoresis, what we have is an electrode or rather two electrodes put there, and we have some charge, some particle with a size and a charge. Okay. This particle is defined with a charge on it and the size of this particle, and depending on the charge and the size, these particle would be pulled towards one electrode. That is the idea here. Obviously, you can you will appreciate that if the charge is highest and if the size is smallest, the particle will attain the highest velocity. Typically, the velocity is attained within few in a very short time. Now, what is the why it should not be accelerating all the way? Because there is a balancing force which we refer as drag. So, basically it would be the pull by the electrode and that would be balanced by the drag force. So, these two forces, they counterbalance each other, and when these two forces are balanced, these particle would be attaining a constant velocity. It is like you remember that settling terminal velocity during settling and those kind of things. So, it would be you need to take this in a similar context. So, you have this particle which is moving at a velocity, and at the same time it is experiencing a drag, and these two forces are balanced, and this defines the constant velocity the particle attains. Okay. So, if there are several such particles of different sizes and different charges, then if you experience these ensemble of particles, okay, with this mixed crowd, if you put them in between the two electrodes, then these and if you expose them for certain amount of time, you will see that particles of same size or particles of same charge, they would be moving at the same velocity. So, you would be classifying these particles within these medium, that is the idea. So, which particle reaches the other end, or you can have a calibration done, and using that calibration you can identify the particle. Okay. So, this is basically the method that is used in electrophoresis. So, if I try to articulate what this process is about, I would like to write it as, in electrophoresis, the topic for today, the first is electrophoresis. Before we go to the other item, dielectrophoresis, here this in electrophoresis, what we have is induced drift motion of colloidal particles or molecules suspended in polar solutions Okay. Now, this induced drift motion is possible because of an application of electric field. So, this induced drift motion, this is possible because of an electric field. Okay. So, this is basically the balance. So, this is a balance between. So, this process is a balance between electrostatic force and the viscous drag associated with the resulting motion. So, electrostatic force and viscous drag associated with the resulting motion. So, these are the two forces, they balance each other. Now, because of small size and low Reynolds number, you cannot expect that the particle will be moving like a ballistic ballistic item. It is like small. So, it would be like low Reynolds number, small size and low Reynolds number. So, this means that Stokes model can be used. So, if Stokes model can be used, then this drag force can be given by the Stokes model. So, what you would be writing in that case is that Q into E, Q is the charge on that particle and E is the electric field, that has to be equal to F drag, that is the drag force, and this drag force is given by 6 pi eta a u e p. U e p is electrophoretic velocity, that means the velocity attained by the particle at steady state. I mean, we said that at steady state these forces are balanced, and so at steady state it reaches a steady state velocity, and this is an observation that it reaches a steady state velocity very quickly. So, this is that steady state velocity u e p. So, this is the definition for drag, and as a matter of fact, I think it should be then that it is actually this should be equal to minus F drag. These two forces are the sum of these two forces is equal to 0. So, Q is equal to minus F drag, which is equal to this quantity. So, and this Q, the charge, this is basically, I mean, you can write this as Z into E. What is Z? Z is the integer valence number. Z is equal to integer valence number, and E is equal to elementary charge. The value of E I have already indicated in my previous classes, previous lectures. So, you need to go back to the notes. E is the elementary charge and Z is equal to integer valence number. That means, if we are talking about some ionic dissociation, then it is whether it is plus 2 or minus 2. For example, CaCl2, it would be plus, the valence number would be 2 in that case. So, it is like that. NaCl, it is the valence number is 1. So, this Z signifies that. So, this Q is equal to Z E, and you would be writing it as Q into E is equal to this quantity. So, in that case, you can write U E P, that electrophoretic velocity, that is equal to, you can write this as Q divided by 6 pi eta a into E. By the way, you understand this, the other components of the drag force. I mean, I am sure this comes from Stokes law. It's a in fact, if time permits, we can discuss this, how we have gotten, because this is a very general treatment. I mean, it is not specific to a microscale process. So, I am not I mean, I am not talking about it here. This is a very basic definition of drag force using Stokes model. Eta is the viscosity within which the, in fact, we have discussed this Stokes model while defining diffusivity, I remember, right, when we defined diffusivity at the very beginning of this course, Stokes-Einstein formula, there we talked about this formula. Okay. So, we have discussed this before. Eta is the viscosity of the medium, okay, and A is the radius of the particle, So, 6 pi eta a and u e p is that terminal, the velocity, that steady state velocity this particle has reached. So, this is then u e p, this is the formula. So, what does this u e p means? U e p in that case, u e p is proportional to q and UEP is inversely proportional to a. So, that means this velocity depends directly on the charge. If there is more charge on the particle, then the particle would be attaining higher velocity, and if there is less charge on the particle, it would be moving slowly. On the other hand, if the diameter of the particle is small, then it will have a higher velocity. So, if there exists a mixture of particle, some are big, some are small, some are having higher charge, some are having lower charge. So, they will attain different UEP depending on their size and charge, right. So, if you expose them for some time within this system, you will see that particles of certain size and charge, they will be moving faster than others. So, they will classify themselves. So, that is exactly what we are looking at. Now, this liquid should be of low electrical conductivity, that is one criteria we have here. The liquid should be of low electrical conductivity. A good example of low electrical conductivity would be deionized water. So, if you have a sample, you should put it in, I mean if you expect that sample which is containing particles of different sizes, and if you expect those particles to be attaining different velocities, then in that case you should be putting it in a medium which is having low electrical conductivity. An example would be deionized water. And because this low electrical, if you do not have low conductivity of the liquid, low electrical conductivity of the liquid means basically this implies there is lack of ions, and these ions, if there is more such ions available from the medium itself, then these ions would have accumulated around the charged particle and partly neutralized its charge. So, if there are several such ions already available from the medium, so they would be getting attached, or they would have accumulated around the charged particle, and they will partly neutralize its charge. So, it will not be so you will be working with a less Q in that case. So, you will not be getting the level of sensitivity or the level of motion that you can expect otherwise. So, it is important that you expose it to the deionized water, and typically this process is within a very short time scale. Very short time scale means within few microseconds. Microseconds means 10 to the power minus 3 or 10 to the power minus 6 seconds, 10 to the power minus 6 seconds. So, within a few within 10 to the power minus 6 seconds, they reach steady state. These particles reach steady state. Okay. So, this is what basically what we have as electrophoresis. Now, there is one issue here, is the size of the particle is important here. If the size of the particle is large, if the size of the particle is large means how large? What is the definition of this large? That is there, that problem is there. So, the idea here is you have an electrode, or you have a set of electrodes, you have a particle. Okay. Now, if this is a small particle and this has this is the dipole length, in that situation, this can be one case, and the other case could be you have a set of electrodes and you have a large particle and the dipole length correspondingly is smaller. Okay. So, there are two such situations possible. So, here it is plus, here it is minus. So, you have connected these, and here also you have this is plus and this is minus, and you have connected this. Okay. Now, here this charge is say plus, here this charge is plus. So, this would be attracted, this would be moving towards this direction. Okay. Now, this distance is, I said, d by length. So, that you look at the radius of the particle or diameter of the particle, and that is small compared to lambda d, the d by length. Lambda d we have already discussed in connection with electroosmosis or electric double layer, right. So, this is that same lambda d we are talking about. So, you have two situation, one is d much less than lambda d, another situation where d is much greater than lambda d, okay, because this is lambda d. Bottom line is basically the one, in one case the particle is small and the other case particle is big. What is an example of a big particle? Big particle could be, say for example, this particle we say is, I mean we are talking about large solid particles. Of dimension 100 to 10,000 nanometer diameter. Polystyrene spheres, single celled organisms, clay particles, Okay, so, here in these cases we have said that this d is much greater than lambda d. In that case, the ionic cloud near the particle surface can be ionic cloud near the particle surface can be approximated by electric double layer relations for a flat plate. And then in that case u would be equal to epsa zeta by mu into E. Do you recall this expression? We have used this expression. We have used this expression in connection with electroosmotic velocity UEO. We have talked about this expression before. You remember this we have that 1 minus that cos hyperbolic something divided by cos hyperbolic h by 2 lambda d. So, that expression was there, and we said that for a major part of the channel this is the velocity that is prevailing. So, this was UEO, that time we referred this as UEO, the electroosmotic velocity. So, here what they are saying is that since this particle is large and this dy length is small, so the ionic cloud near the particle surface can be approximated by EDL relations for a flat plate. And then the velocity, now this UEP, this electrophoretic velocity for this particle is nothing but the velocity, electroosmotic velocity of this double layer. That is what they are, that is what the argument here is, that the particle is too large. So, the double layer that is formed around the particle, what would have, what would be the velocity of that particle. So, that would be governed by this electroosmotic velocity, and that is what would be governing the motion of this particle. That is how the treatment would be. So, and this when d is much less than lambda d, this is the classical case of electrophoresis. We have already defined this. What was our formula then? U is equal to what did we say, q divided by 6 pi eta a into E, right. So, this is the formula that we already found here. This is the formula that already we have found here by using by balancing the two forces, electrostatic force and the viscous drag. So, so this formula would be valid when you have d much less than lambda d. That means, diameter of the particle is much smaller than the dy length, whereas when the diameter of the particle is large compared to the dy length, in that case this ionic cloud near the particle surface can be approximated by ideal relation for a flat plate, and the movement of this layer would be governing the velocity of the particle. So, these are the two equations we have now. Now, one thing you must note here is that in this expression we do not have any diameter of the particle involved, right. In this case we do not have any dimension of the particle. So, this is so basically what we are talking about is two regimes. This is one regime and this is another regime. In this regime, when d is much greater than lambda d, the effect of particle size is not there. I mean, dimension of the particle does not, I mean, whether it is this big or little more, a little bigger, they will not, that will not affect the velocity of the particle. So, based on the particle size, I mean, suppose you have particles of same charge, but of different sizes, but if you are in this size, if you are in this regime, you cannot differentiate, you cannot I mean, this will not help you. That is what it says. Okay. But anyway, we are talking, here we are talking about the molecules, etc., and here we are talking about what you call large solid particles, polystyrene spheres, single celled organisms. So, these are a different dimension altogether. So, this is I would say all I had as far as the electrophoresis is concerned. So, you more or less you have some background in what we have, what we are talking, I mean what we mean by electrophoresis and how the treatment would be. If somebody wants to know that what would be the velocity and what would be the extent of movement of particles of certain charge and size. Now on top of this, I mean I do not know whether I mentioned this in the beginning in the introduction lecture, is that on top of this they have something called a gel electrophoresis, where in the medium itself, I said it should be deionized water, right. The medium should be deionized water, and within that the particle should be moving. Instead of deionized water, people have used hydrogel, okay, which is a matrix, gel matrix. You have some idea of what a hydrogel is. I mean, I am sure you have that. It is basically it is predominantly water with some polymer and cross linker put together, so that it forms a network. It forms a polymer network within which the water would remain trapped. Okay. And now these ions, they can move through these, or the molecules, they can move through these gel network. If you take a gel and if you put a ink on top of this gel, you will see the ink is percolating. It is diffusing into this medium. So, that means it is acting like a porous matrix. Okay. There would be diffusivity, but that diffusivity would be scaled down. For example, if you are looking at say an ionic diffusivity of 10 to the power minus 5 cm square per second in water, in water, if you look at that diffusivity, then when it comes to a hydrogel, which is predominantly water with some gel network, you would be getting a diffusivity which is an order of magnitude less, because there would be some amount of tortuosity though these molecules have to encounter while diffusing through this medium. because of this porous structure. So, some people have or there it is a convention in some places to use gel instead of deionized water. So, in that case gel offers extra screening. I mean, particles of certain, suppose you have particles of different sizes and you want to screen. So, particles of certain sizes, gel will not allow those particles to pass by. Gel offers another level of screening. One level of screening is, you know, that electrophoretic velocity would be depending on surface q, the charge on that particle. Electrophoretic velocity will depend on the size of the particle. On top of that, there would be another mesh sitting there, it will allow only particles of certain sizes. So, that is referred as gel electrophoresis. So, this is people who are students who are connected with biochemistry or biochemical those sort of applications, if you are working with, you will see this kind of gel electrophoresis it's very common. Anyway, with that I conclude the discussion on electrophoresis. The next topic that I pick up is dielectrophoresis. I refer, this is would be referred as DEP, dielectrophoresis, and this is a different concept. It is not electrophoresis, not an extension of electrophoresis even. It is a different thing. This now before we get into this DEP, I would revisit. I mean, I keep writing this. I have written it at least 2-3 times before, but still I mean, let me. There is no harm in writing it once again. I write this Navier-Stokes equation once again. And let us try to understand something called polarization process, which is known as polarization. What is this polarization? A small particle, such as a biological cell occupying, suppose this occupy region omega in space, centered around the position vector r0, having electrical charge density rho EL. What do we have now? A small particle such as a biological cell occupy region omega in space, centered around the position is the position is given by r0, position vector is r0, having electrical charge density rho EL. Okay. So, in that case you have this as the body force term you have considered before, where this rho EL and electric field E, their product, this is acting as a body force term in Navier-Stokes equation. Okay. Now, if we try to look at this body force term, now focus on this body force term. Body force term will have this will have I, j, k components, and if somebody wants to write this body force term, it would be like body force term would be, since we are talking about a region omega, then this should be generally the body force term would be dr rho e l e for the entire region omega. So, that is what the body force term would be defined in this case, since we are looking at a region omega and not just a point. So, if we talk about the ith component, then this would be equal to this would be equal to so what this would be this expression would be there for the ith component of this body force term. So, you have a particle occupying a region omega, this is something which is new here. So, if it is occupying a region omega around the position vector r 0, so for all such points around r 0, so what is r 0, what is r plus r 0 or rather r 0 plus r, what is this? This is a general position inside the particle, inside that biological cell. Inside the biological cell there are several positions, and those individual positions are given by r 0 plus r. R 0 is fixed, because r 0 define the center of that region omega. Around that center there are several r's. So, you have to take into account them. So, this r 0 plus r is a general position inside the particle. So, when we are talking about the ith component, we are talking about these E I, all right. So, this is the expression for the force in the ith component of it. Now, this if we go for a Taylor series expansion and ignore the higher order terms, Taylor series expansion would be then F I E L would be equal to, this part remains same. Let me use another slide, sorry. Taylor series expansion will give this part remains same, it is remains unchanged. You are expanding the E term around r 0, okay, around r 0. Do you let me write the next step also, then I will get back to how we expanded this. Well, now this is the framework. I mean, we will get into this discussion later. Don't bother about it. I said that I have made an Taylor series expansion of this term EIR 0. Okay, what does this term mean? I mean, if you expand this term, how will it appear? It will appear something like this, right? For the 3 components, you have to expand these EIR 0. So what exactly you are doing? Around point R, you are doing a Taylor series expansion of the field E. So a general vector is R 0 plus R. So from this point R 0, say this is a new, this is a different, this is the local difference. Suppose this is the region omega, this is the center R 0. Around center R 0, you are expanding E. So any point, any other point R 0 plus R, if you try to find out what is the value of E at that point, you are using this Taylor series expansion for that purpose. So you need to find out. So you have to take the first derivative of it, del E I, del x, del E I, del y, and multiply that with the corresponding R. Right. So that is exactly what we are talking about here. It is a Taylor series expansion in a which has more than one dimension. All right. So make sure that you understand this, and if we do not, then we can probably discuss this once again later. So basically, we made a Taylor series expansion of this E term. What did we have earlier? Then it will be clear. What did we have earlier? We were talking about this expression phi EL is equal to integration. This part remains same. This part we are not touching. This EI R plus R 0. So EI R plus R 0 is expressed as EI R 0 plus H f prime x plus h square by 2 factorial f double prime x. So that is what we are looking at. Higher order f double prime x and all those are all neglected. I mean, h square term onwards neglected. Only we are focusing on h f prime x. But since it has multi dimension involved, so it would be taking the shape of this. Then you would be writing this. So you have two things here. One is this and this. You are clubbing them together and calling it Q E I R 0. What is Q then? Q is nothing but integration dr rho E L R naught plus R. So you are clubbing this. You are clubbing these two terms or this term. Another is this multiplied by this. So you are basically taking this third bracket off, multiplying this with this, multiplying this with this, and you are getting these two terms here. One is Q E I R 0 and another is P j del j E I R 0, the derivative of it. All right. So you have these two terms where Q is equal to integration dr rho E L R naught plus R. And what is that now? That is referred as charge of the particle, no doubt about it, rho E L into rho E L dr. So you are basically summing rho E L over the entire region omega. So that is basically charge of particle, and P is charge multiplied by the corresponding position. This is referred as electric dipole moment of particle. I mean, we do not need to get into the, I mean, we can get into the definition of this later, but one thing I want you to appreciate here is that if the Q is equal, if Q is equal to 0, if Q is equal to 0, okay, if Q is equal to 0, if we look at the Navier-Stokes equation earlier, if Q is equal to 0, then you would have called this term is not there. I mean, you have, our understanding is q is equal to 0 means what? Over this entire region omega, the net surface charge, I mean, what is q? Integration dr over the entire domain omega, rho el r naught plus r. So, sum of all the individual charge densities at various points, and if the net charge of that particle is 0, in that case our understanding is that this is incapable of giving rise to any body force. That is what our understanding was. Now, the point here what I am trying to make is that I mean that is I mean I am talking about an electric field, I am talking about a particle sitting there, and within that particle, within that entire omega, the net q, if I sum all those individual rho el r 0 plus r, if we sum them over that entire omega, I found that that is 0. Our immediate conclusion is there is no charge on this particle. So, this particle is not ready to give rise to any electric any such body force, electrostatic body force. So, we do not have that, we do not have to bother with this. Okay. The one catch here is that this E term, the capital E, we assume that the electric field is uniform, but what this analysis, what we said here, this analysis says is that even if q is equal to 0, if P j and del j E I are 0, if these two terms are non-zero, if these two terms are non-zero, then still there can be a body force F I E L possible. All right. That is what this I am trying to drive at. Okay. So, what does this mean? That I have P G A non-zero, and particularly what does this mean, this term? Do you have any idea what this is? What this means is that the gradient of the electric field is non-zero. Gradient of electric field is non-zero. Okay. Gradient of electric field non-zero means delta E, this is non-zero. This delta E is non-zero. Delta E is non-zero means the immediate response would be this is non-uniform electric field. How do you get a non-uniform electric field? I mean, I am familiar with uniform electric field. I have one, we have been discussing so far, so many drawings we made, one electrode here, another electrode there, all uniform. If you draw those lines, they are all straight lines, right. So, how would you get a non-uniform electric field? If you can get, I mean, the idea here is that what the people are driving at is, if you can get a non-uniform electric field, there is still a force it can deliver. There is a force possible. Of course, still this P j has to be non-zero. They club together, they can give rise to some body force. Okay. But how will you get a non-uniform electric field? In this process, in DEP, always DEP you will find there would be two electrodes, one electrode would be planar electrode, another electrode would be a point electrode. Okay. There would be a planar electrode. So, these would be the lines. So, this is one electrode, this is the planar electrode, and this is the point electrode, and that is how you create this non-uniform electric field. All right. So, first of all, this you get that is how you ensure that this delta E is non-zero, number one, that means del J E I R 0, this term is non-zero, and then this P j term has to be non-zero. P j is what? This electric dipole moment of particle, this term also has to be non-zero. Okay. Then in that case you would be writing this F, what do you want to call it, dielectrophoresis, FDEP. FDEP, I think we will give a different FDEP we will discuss in different context, but I can put it this way, it would be P dot delta E. This is the definition of the force in this case, P dot delta E. Exactly, that is what we are talking about. Q is equal to 0. Q is equal to 0. So, this is the term that is contributing to the force, and Q is equal to 0 means this particle does not have any net charge. Okay. This particle does not have any net charge, but still if we can attract the particle towards one electrode or not based on certain properties of that particle. Particle may not have to have some charge on it. Okay. So, this DEP, let me tell you, I mean before getting into these theories further, this DEP is there is a very common method, I mean the common way of using DEP is something called DEP trap. You have several particles flowing through the stream and you want to trap certain particles based on their properties, and the particles they may not carry net charge. Net charge on the particle, the Q is 0, the total charge on the particle is 0, but based on the properties of the particle, okay, based on the properties of the particle, and you are intentionally creating a non-uniform electric field. By that way you can basically impart some FDEP, you can impart some DEP force on that particle, and that force can act against the drag of the particle. These dielectrophoresis, this is employed to separate live cells from dead cells. Suppose somebody is doing an analysis of some say pathogen, and it is flowing through a microchannel, and you want to know how much is the first of all you want to separate the live cells from the dead cells and want to know which are really the active cells, because if you measure the number of dead cells there, I mean anyway they are dead. So, if you want to separate if you want to separate them, so based on the properties of the cells, if you see the properties of the cells changing, if you see the property of the cell changing, so you can based on that you can trap the particle. That means, this particle when it is flowing through the channel, if you have to so there is a drag force the particle is experiencing, because it is flowing through the microchannel. So, there is a drag force, this particle is that is the fluid is imparting on that particle, on that say cell, on that biological cell. Now, you are imposing a DEP force on this. So, you are acting against that drag force. Now, depending on the property of the particle, some particles the DEP force that you impart is more than the drag force. So, you retain that particle near that electrode, near the point electrode. So, you have a channel, you have on top of the ceiling of the channel is a planar electrode, bottom of the channel is a point electrode, and you have other accessories downstream, upstream, etc. When the fluid with these biological cells, they are flowing through the channel, then depending on the property of that cell, some cells are held near the electrode, some are not. So, that is one major that is what this DEP is going to do, then that this DEP trap. Also, this DEP is used in context with field flow fractionation. That means, this DEP force will be acting to settle the particle at certain level within the channel. So, that is another way this DEP can act. Now, what we will be doing in the next class is we will be discussing this. We will be coming up with some understanding of what should be the velocity of the particle, and given the properties of the particles, and the velocity of the particle, what should be the velocity of the particle. That means, at what velocity these we should have, what should be the fluid velocity such that you can trap the certain particles with these properties. So, we need some theory, we need to understand what should be the how we relate this DEP force with the drag force to come up with those understanding. So, that is something which we would be looking at in probably in next class. We will I think in the next class we will be able to do that. In the next class we will be defining this those velocities and those theories behind, I mean, how we can theorize this part. So, then that we will be looking at, and also we would be I would like to I mean I will show you which I mean what we have this property called EPSA. If possible, when you come to the next class, you study these property EPSA that we have been talking about so far. What is this EPSA? EPSA of a medium, dielectric constant. What is this property? So, you try to understand, because this is the property that would define, this is the property, or rather the relative I mean we have dielectric property of two things involved. One is dielectric property of the cell, another is dielectric property of the medium within which the cell is flowing, and these two dielectric properties combined, they will determine what should be the force, dielectric force on that particle. So, if possible, when you come to the next class, have some try to get some understanding of this property EPSA which we have been talking about so far, because this is going to be very crucial in this analysis. And keep this at the very keep this very clear that here the q is 0, this q is 0. So, you have the way we have defined this in Navier-Stokes equation, the conventional this body force term, there we have assumed that there is a uniform electric field. When we talked about this electroosmosis and all this, we have talked about an uniform electric field, and there is a rho EL present, and they have given a body force. Here this component is 0. So, ideally this there should not be any body force, but the body force is arising because of that P term, not the Q term. So, this you have to have very clear in your mind, that unless you have a non-uniform electric field, the you cannot create DEP, because your net Q is 0, and yes, your net Q is 0. So, that is very important in this context. Yeah, that the other thing that I have been forgetting is that the beauty of this method is you can use the AC. I mean, you don't need a DC supply. You can have AC current, or I mean the voltage can be in alternating mode as well. So, in that case, if the liquid that has certain ions, that will not be affecting the process at all. I mean, suppose we said that deionized water and those charges, etc. We have been talking about, we have this problem. I mean, we know this, that the medium should be totally inert medium, but here in this case you can use an AC field as well. You can use an AC electric field. That means, the point electrode and the planar electrode, you do not have to apply a DC voltage between them. You can use an AC voltage as well. I will probably give you some idea. If you impose AC voltage, it will not affect much the process. I mean, it will be a different formula, but still this process will work. And but the beauty of it is, if you use an AC field, then you do not expect the charges which would have been otherwise moving to the electrode, getting into the process of electrolysis and all those kind of concerns will be gone if you use an AC field. So, that is the beauty of this method. This is a very powerful method. We will get into this in the next class. Thank you very much.